So anyway, we know that the surface of the moon is pretty complex chemically, and there's a lot of evidence for these complex magmatic processes, but I want to take you to a place where we might think that there's some of this complexity it prevails at a much smaller scale and within one particular system, and it's in the Snake River Plain. We have done a lot of work on the Snake River Plain, analyzed hundreds of rocks, but we're going to focus now on the Great Rift, which is right there along, let's see, I don't know which one of these is the pointer. Oh, separate. Of course. Okay. All right, so Great Rift comes right along here. It encompasses craters of the Moon, National Monument and Preserve, Kings Bowl, and Wapai Lava Fields. And in particular for today, we're going to talk about some eruptions from the north end and the south end that all occurred at about the same time. And that's important because it's all this compositional diversity right at the same particular period of time on the same rift. We've got several flows up on the north end, the highway flow, north crater, big crater, serrate flows, which are kind of morphologically distinct. Okay. And then we got Kings Bowl and Wapai lava flows, which are pretty much low shields. Kings Bowl is an aborted low shield. They have quite diverse morphology, as I said, pretty rugged topography, especially the highway flow and the serrate flow. But whereas the flows at the south end are fairly smooth and just like you'd find any good pohoihoi olivine tholite. Well, chemically, they separate into three groups. The highway serrate group, the North Crater Big Craters group, and the Wapai Kings Bowl group. Here on a task diagram, we got basalt, trachy-basalt, which is Hawaiiite, and latite, trachy-dacite. So we want to look at these in more detail, and more recently we've just done a study of Kings Bowl, where we have analyzed rocks from the whole system. It's about 7 kilometers, and we see quite a bit of chemical diversity in this whole system. You can see that magnesium, iron span quite a bit of compositional range just in this very small eruption that occurred probably within a few hours. And so how can we get that compositional diversity? But that's just one part of the story. We want to look at the compositional diversity amongst all these units there. And so the evidence from trace, that's supposed to be major elements. Major elements, we see that at the north end of the Great Rift, we have high phosphorus, higher potassium, low phosphorus. The south end, we have low potassium and moderate phosphorus. We have high titanium at the north end with the North Crater and Big Craters, and at the Wapai Kings Bowl system, and quite low titanium down at the highway serrate flows. So there is quite a bit of difference between these, and it sort of argues for multiple magmas or one magma that's evolved into multiple things. And so it's kind of difficult to get to have them both, but I think it's really much more complex than we can just you know, say right off the bat. Anyway, with evidence from trace element geochemistry, thorium variation, high thorium in the highway serrate, low thorium in the Kings Bowl, as you'd expect. But you can see that these don't fall on one trend. They fall off the trends. And so there's got to be a way of getting these things sort of together in one system without, and on one rift system within a short period of time. And so you can see that zirconium versus silica, there is sort of maybe a trend in there somewhere, but we want to look at some more detailed models. And one of these types of models is just a simple model where we look at one major trace element that's incompatible versus a major element that's compatible like this. And we can pull up these contrived models and do some mixing lines and things like that. And this is just an example of the combined, but we can see that we can plot the highway serrate flows, the North Crater Big Crater flows, and the Kings Bowl Wapai flows on this kind of a model. But I want to look at this in a little bit more detail. This particular model shows magnesium versus titanium, and it's a combination of a Meltz fractionation model at different pressures, plus mixing lines, but also plotted on here is the graveyard point sill, which actually occurs on the Snake River Plain. It's pretty much the same kind of a composition, and it follows pretty much some of these fractionation lines that we get. However, we can't predict entirely the whole realm of compositions just with this Milt's fractionation. We do see that the wide range in the tholeiites, like King's Bowl and Wapai, produce a nice trend, but we can't predict that trend with just simple fractionation. It just doesn't work. So we do find that the chemically evolved lavas and cones, like North Crater and Big Crater, plot right in here, and we can get those in there. We have domes, silicic domes, and the highway and serrate flows that plot there at the low magnesium end, that examples of that extreme fractionation. Looking at another one of these, another example, zirconium versus magnesium, we find out that just with a very simple plot here, because zirconium we are assuming it's so totally incompatible that it doesn't go into anything until somewhere very late stage. It might produce some zircons. But this graveyard point sill shows a nice fractionation trend following, behaving itself with the Milt's curves and at mid-crustal levels. And so, and there's also quite a bit of evidence on the Snake River Plain for a mid-crustal sill to produce all the other samples or all the other eruptions on the Snake River Plain. So we have this wide-ranging composition that's related to the intrusion of multiple sills, multiple intrusions, layered mafic intrusions on the Snake River Plain, through which other magmas have passed through and mixed. Now, this mixing is not just simply magma mixing. It's where you have what we propose is that you have an intrusion, a sill-like intrusion, that it starts to fractionate, and as it starts to fractionate, it builds up the incompatible elements, as you'd see here. But at the same time, another injection of a similar magma from the same source, perhaps, starts to work its way up through and thermally erodes, thermally absorbs, and extracts trace elements, for example. And so we get a mixing line like this. The whole Craters of the Moon trend falls on a nice mixing line between the primitive magmas down here and the more evolved, highly evolved compositions up there. These would be the domes and the very evolved Craters of the Moon samples. These would be the tholeiites like Wapai and King's Bowl. So what does that say for the Moon? I mean, it suggests that some of these features that we see on the Moon, we already know that they're going to be chemically evolved, and we're starting to find out all what we've been hearing today, yesterday, and the day before, that we got these, this compositional diversity with, say, domes surrounded by Mare. And I think that some of the processes that we're seeing at the Snake River Plain could be certainly applied to these situations on the Moon. Marian domes. I mean, Tim, this is really good to see that you've actually identified the silicic domes. We have there's a East Dome and Big Southern Butte. East Butte and Big Southern Butte on the Snake River Plain, which are clearly silicic, sitting right in the middle of olivine tholeiites. And so and here we have the same kind of a system, the volcanic features derived from silica-rich, chemically evolved magma surrounded by Mare basalts. We also have floor fracture craters. Now, I don't know if there's much evidence at present for extreme amounts of chemical diversity in the floor fracture craters, but I'm suspecting that because we have systems that are similar to, say, King's Bowl fissure eruption, that we might start to see that there's maybe some chemical diversity along the rift systems or within the lava flows or pyroclastic deposits that are associated with these eruptions. And what we envision is instead of just a simple eruption through a fissure, we have the injection of layered mafic intrusions, multiple injections, multiple fractionation events, and multiple injections of primary magma that kind of mix in with these and sort of extract some of those chemical components that need to be that cause that chemical diversity. So anyway, we think of this as in a general magmatic model. A proposed analog would be just that. The primary magma is injected in the shallow subsurface. The layered intrusion leads to chemically evolved compositions. Compatible elements are diminished in residual liquids, yet they're replenished by those multiple eruptions. multiple injections of fresh magma, and then we got these magmas that are derived by mixing of evolved and primitive compositions. And so we see that those processes would certainly occur on the Great Rift. And what we have going on for us now is we're going to continue sampling. These are the places where we've sampled in yellow, where it has a red halo around it. We've analyzed already, but we want to collect more, analyze more, but at the same time work on collecting in situ data with portable instruments, portable XRF, LIBS, so that we can calibrate those instruments for the field work and actually determine what sort of chemical variability we have within the flow and along the flows, like that. And so that's what we think is going to be the importance of doing this, these field investigations as an analog to doing lunar research. So in conclusion, I'll let you read that. Chemical variations provide evidence for these complex processes, and the models support commingling of primary magmas and evolved components most likely derived by fractionation. But the implications are, I think, are the more important here. Magmatism along volcanic rift zones can be composition and complex, need to closely examine those possible chemical and mineralogical variations. And I think we need to do some high-resolution sampling. We need to get back and start looking at lava flows on the ground on the moon. Thank you.
Okay, this paper is open for discussion. Do we have some questions or comments for the speaker? Yes, is that Paul?
Yeah. All right.
Paul Niles, JSC.
Yeah, Paul Niles, JSC. So, Scott, what do you think? Do you think that there's something particular about the sort of geologic setting, you know, in the Snake River Plain that gives rise to this sort of behavior? So the formation of these sills and you know, multiple magma injections through the sills.
That's a really good question. I didn't allude to that, of course, but it's in the wake of the Yellowstone hotspot. But the Yellowstone hotspot was out there 10 million years ago. It's not directly related to that plume, if you will. I think it was a thermally evolved lithosphere, thermally weakened, and it's been subjected to extension by basin and range extension, and that extension allows for decompression melting. So regardless of the mechanism of melting, we've got a crust that's kind of foundering. It's almost like, I would think, like the Great Rift is almost like the East Rift Zone of Kilauea, where it's a magmatic rift system that has a lot of eruptions along it. And most of the dikes that are injected in the Snake River Plain are all oriented in a particular direction, which is perpendicular to the extension.
And so what would you say about the moon from that? Is there, I mean, does that tell you something about the nature of the geology of these areas where you get these silicic domes on the moon?
Well, I kind of like the idea of having the crust kind of weakened up somehow and maybe thinned out a little bit. But other than that, I think that we do need to have shallow intrusions.
Other? Yes, Tim Clash.
It's just that last point. Almost all of the silicic features, I think everyone with the except on Compton-Belkovich is in the Procellarum creep terrain. You know, so you have a higher heat flow, thinner crust probably. I mean, so that could be consistent with what we just said.
Oh, good.
We have time for another question if one exists.
Gosh,
Don't be shy. Got time.
getting late.
I guess it is. They're all anxious to hear Alan Stern's story.
Yeah.
Okay, thanks, Scott.
Yep.